Grade 12 learners, there is a great disturbance in the force. To get to the top, a straight path we will not follow. Question 1 of your final Physical Sciences Chemistry Paper 2 will be made up of a set of questions that are multiple choice questions. These multiple choice questions will test different topics in your chemistry section of the Physical Sciences. The question reads as follows. Various options are provided as possible answers to the following questions. Choose the answer and write only the letter A to D next to the question numbers 1.1 to 1.10 in the answer book. Then there's an example there where they say 1.11 and then they write E there. This is just to show you how you should write your answers. They're saying that you shouldn't write the statements. You only write the letter that is provided. Question 1.1 says, which one of the following compounds is inorganic? Remember that we have organic compounds and inorganic compounds. Organic compounds are made up of carbon and hydrogen, or carbon bonded to other atoms. Now, if we look at these options that we have here, we can see that with option A, that looks more like a organic compound because I can see some carbons and hydrogens and also some alcohol, the OH. In fact, if already you know this, you can see that this is a propanol. If we look at B, I see some hydrogen and carbon bonded together and there is some bromine there. This will give me a methyl bromine because I can see that this is an alkyl group. If you look at C, this is part of the CFCs, the chlorofluorocarbons, right? Which we all know that they are part of the hydrocarbons, right? Even though they are not comprised, we have a carbon bonded to a chlorine, right? We don't have the hydrogens in this specific one. And maybe you know this or you don't know. This is called methane tetrachloride. Some people like to call it benziform. It has many other names that people use to identify or classify this type of compound. Already by default, we can see that D must be our answer because all of these are hydrocarbons. But let's have a look and see if it makes sense. I mean, if you look at D, it's a compound called sodium hydrocarbonate. It's a sodium hydrocarbonate. It's part of the hydrocarbonates, right? Some people call it sodium bicarbonate, right? So our answer to question 1.1 should be D. Now we'll jump to question 1.2. Question 1.2 says the hydrocarbons consist of alkanes, alkenes, and alkynes. Which one of the following is the general formula for the alkynes? Now, obviously, this will require you to know your notes. If you forgot this or you don't know about this, go and revise this. But I'll just assist here by giving you the answers to this one. If we look at this first chemical formula, we can see that this is an alkyne. It's the correct one because an alkyne, you subtract a 2 there, right? So our option is that one, is A. I'll write this option and explain to you how to identify this. If you look at the option C here, is what we call alkanes, because what it says that, let's say you have two carbons, N would mean the number of atoms that you have. Let's say we have two carbons, it means also here we'll have two. So 2 times 2 is a 4, you get a total of 6. So that means you have two carbons and you'll have 6 hydrogens, right? And then if you go to B, for instance, you would see that this one is what we call alkenes or alkene, right? If I'm using the example of having two atoms, right, I'll have C2, but look at there at the bottom, it will be 2 times 2, which is a 4. Do you see that now the number of hydrogens are getting smaller? In fact, that's how we identify saturated carbons and unsaturated carbons. So saturated carbons is when you have the largest number of carbons, as many carbons as possible, and here you have less carbons. The reason being is because here we have a single bond, or on the alkanes we have a single bond, but when you go to the alkenes we have a double bond, right? And here, you know, the reason why we call this the alkenes is because now if you have two carbons, you have the smallest number of hydrogens. It will be 2 times 2, which is a 4, minus 2, you get a 2. The reason why the hydrogens have been reduced is because we have triple bonds in here. When you draw this, it will be triple bonds, right? Becoming highly unsaturated, right? So that's how you identify them. This one doesn't exist. Now I'll jump to question 1.3. 1.3 says the alkane propane is flammable in its reaction with oxygen, right? Now they then come and say which one of the following is the correct balanced chemical equation for the reaction that takes place, and they give you those options. Now to tackle this question, I think you have to look at the keywords. Of course, this is an alkane, it's a propane, but also they say flammable. When they say flammable, it means here they're giving you a clue to say we are dealing with a combustion reaction. We are dealing with a combustion reaction, right? And we all know, I think, or I believe that at this stage, we all know that combustion reactions, they always give us a product of carbon dioxide and water. That's how we identify combustion reactions, right? And a propane is a very common type of gas that we use in our homes, right? To cook. We use it to cook. Gas stoves, they use propane, for instance, right? So propane is made up of 3 carbons, right? So it will be C3H8, right? Because now if you have 3 carbons like that, it will be attached to 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. That's why I'm writing it as C3H8, right? But of course, we're saying now here it reacts with oxygen. So what's left here is to balance this equation, right? In order for us to balance this equation, I'll start off by looking at my carbon. I have 3 carbons here, and I only have 1 carbon here, right? This means I can put a 3 here. This means I can put a 3 here, so that now I have 3 carbons and 3 carbons. Now they're balanced. Now I focus on the next atom, which is hydrogen. If we look at hydrogen here, I have 8 hydrogens and I only have 2 this side. What can I do in order for me to have 8 on this side? Well, that means I can put a 4 here. Because now if I put a 4 here, if I put a 4 in front of the H, it then means now I have a 4 times 2. It gives me a total of 8. Now I have 8 hydrogens and 8 hydrogen atom on the left as well, on the right as well. Then it means we can focus our attention on oxygen now. Remember, this is a 2 here. There's a 2 here. I forgot to write the 2 on my oxygen. There's a 2 here. Now on this side I only have 2 oxygen, but this side I have 3 times 2, which is a 6, plus the 4, because I'll have 4 times 1 here. This gives me a total of 10. So in order for me to balance this equation, it means this side, I then have to put a 5 here. Because 5 times 2, it gives me a 10. Now my equation is balanced now. All that's left now is to check if I have this equation on these options. There's only one option that has a 3H8 5O2 giving me 3O2 and H for that. So my option has to be D. 1.3 is a D. Now we move along to question 1.4. Question 1.4 reads as follows. It says, in an experiment, turbidity of a solution is used to investigate the rate of a reaction between thiosulfate and excess hydrochloric acid. Now there's a lot of things that they've said here. Let's break this question down. I just want to break what turbidity of a solution is. So turbidity of a solution is a type of technique that we use when we do experiments in a chemistry lab. So when we have a reaction that involves a solution and there is clouds forming in that reaction as the products are being formed, right? So when I say there's clouds forming, it means one of our products will be a gas. Then that gas makes clouds, right? Is what we call turbidity. Those clouds, we can use them to then find or determine the rate of a reaction. How that is done generally is that we take a piece of paper and we draw a cross on that piece of paper. Then put that piece of paper inside the reaction, usually a beaker, and then observe that reaction as it takes place. We'll notice that the clouds will cover that cross. The time that it takes for the clouds to cover that cross then help us to determine and find the rate of reaction. So that's basically how that technique works. So in this case, they say they've given us a thiosulfate, which is this here. And then we have an excess of hydrochloric acid. Now hydrochloric acid is this guy here. Now what do they mean here? Let me try to draw this so that we can have a mental picture of this situation. Let's say now you have this reaction occurring in a beaker like this. And we have from at the bottom to here, let's say is our thiosulfate, right, which is given by Na2 S2 and O3. And let's say from the bottom to somewhere here, we have our hydrochloric acid, right? Now, notice that I've made this to be a lot in this beaker because it is in excess. That means it has a high concentration compared to this. This has a small concentration, right? Now, as this reaction progresses, you'll notice that we'll form a product here, right? In our product, we have a number of things. What you'll notice here is that 1 mole of thiosulfate forms 2 moles of sodium chloride, and also 2 moles of hydrochloric acid forms 2 moles of sodium chloride, right? So we have formed here sodium chloride. We then also have 1 mole of thiosulfate forming 1 mole of H2O, because we can see here the oxygen, when this decomposes, when it breaks down, some of the oxygens will form this guy here, water. And we also have 2 moles of hydrochloric acid forming oxygen as well. forming water, not oxygen, H2O. So this means here we also have H2O being formed. Now this is just a schematic diagram, remember, just to have a mental picture or a feel of what's happening in this reaction. We also then have thiosulfate again, 1 mole of it forming 1 mole of sulfur dioxide. So we have SO2 as well here. But also but check here what's happening now is that the hydrochloric acid doesn't form sulfur dioxide. When this breaks down into hydrogen and chlorine, there's no any atoms that form this. It's only 1 mole of this thiosulfate forming 1 mole of sulfur dioxide. And the same is true with the sulfur here. 1 mole of thiosulfate forms 1 mole of sulfur. And our hydrochloric acid doesn't form any of the sulfur. But also one thing that you have to note is that the reaction as it happens here, when we're forming all these different products, you will notice that when our thiosulfate has been used up, if all of it has been used up here as the reaction progresses, the reaction will stop because we don't have any of this thiosulfate to form any of these products. So the reaction will stop. When the reaction stops, we'll have excess of hydrochloric acid. It means here we'll still have a little bit of hydrochloric acid left because it was in excess. Remember we said here we have a large concentration of this compared to this, right? So when this gets used up, we still have a certain amount of that being left, right? Now that's what's happening in this reaction. And of course we have to note that we have a gas here which will form our turbidity to help us determine the rate of reaction as I was explaining how the turbidity technique works. Now they then continue to ask us by providing options to say which one of the following combinations will increase the rate of the reaction and also the yield of sulfur. When they say the yield of sulfur is that on these factors that they've given us here, which one will make the rate of reaction to be quick for this reaction to occur quickly, but also to make this to be increased, to have a lot of this at the end of the day, right? To have a yield, a lot of a product of this being formed. Right, let's go through our options and see which one will give us those two options: rate of reaction being increased and also the yield being increased. They say here the decrease of concentration of thiosulfate. If we decrease thiosulfate, well, a decrease will make a reaction rate to be slow because remember, we can only increase the reaction by increasing the concentration. So this is out, it cannot help us. They then come here and say the increased concentration of thiosulfate. If we increase this concentration, right, then we'll have a lot of particles in here. We'll have a lot of particles in this reaction of thiosulfate reacting with hydrochloric acid. And this will then make this reaction to be quick because there'll be more effective collisions. But not only that, so the rate of reaction will be increased. But not only that, the fact that we have a lot of thiosulfate now, it means when it breaks, it decomposes, right? It will form more of sulfur. Remember that the hydrochloric acid doesn't form sulfur. It doesn't break into sulfur because there's no sulfur in here. So that's when we'll have a lot of yield when this increases. This looks right. Let's check if we increase the concentration of the acid. So if we increase this concentration, well, if we increase this concentration, what's going to happen is that the reaction rate will be increased, but the yield won't increase because this does not yield that, it does not produce that. So this one does not work as well. Now the decrease of concentration of the acid, well, if we decrease, the reaction will be slow, so this doesn't work. The best option here will be B. So 1.4 will be B. Now we jump to question 1.5. They say here in 1.5, the curve A below represents an energy profile of an exothermic reaction. Well, when we look at this graph, we can see that it's potential energy, chemical potential energy versus time, right? It's a typical energy profile graph. Now, our curve A is this one here. It represents endothermic reaction. It does, because if we look at here, these are our reactants. Remember we said here, this part here is our reactants. And this part here is our products. So here we are measuring the energy of the reactants, and here we're measuring the energy of the products. Now, if we were to calculate here the change in enthalpy, which is the change in energy, right? Because remember here, this is the energy of the reactants, and this is the energy of the products. Enthalpy will be given by the energy of the products minus the energy of the reactants. Now, look at this carefully. If we subtract this part here, which is the energy of the products, from the energy of the reactants, right? Because it's this minus that, you'll find that this is a small number minus a big number. This means here we will have a number that is less than 0, we'll have a negative number. And when that means our change in enthalpy is negative. When the change in enthalpy is negative, that means this is an endothermic reaction. Now, this is just me interpreting the graph to see if it makes sense. They say here curve B is obtained after one of the factors that affect reaction rate is incorporated in the reaction. So what happens here is that one of the factors that affect the rate of reaction is being put into this reaction of this exothermic reaction, right? Then when that happens, our graph suddenly changes and becomes this graph B. It gives us the curve B. Then they say to us which one of the factors below resulted in forming this curve B, which one of these options that we have. Let's go through them one by one. Addition of catalyst. Let's see what happens if we add a catalyst. Well, remember that if I look at curve A here, this part here from here to here, we call it the activation energy, EA. This is the minimum energy that is required to start the reaction, right? So because this is an exothermic reaction, it will begin on its own. It's like if you take two atoms and you put them in a beaker, they will have enough energy on their own to start the reaction. They'll have this energy which will be enough to start the reaction. You don't need to put any external energy like heat or something else to begin the reaction. The reaction occurs on its own. Now, if you look at the second scenario on B, from here to here, our activation energy has become small. Right, the activation energy has been reduced compared to when we were at A. Here it's small. Right, the activation energy could reduce if you put a catalyst. Why? Because a catalyst, remember, speeds up a reaction. It will begin the reaction and speed it up. So if I put a reaction if I put a catalyst in a chemical reaction, this will then make the activation energy to drop. We don't need energy to spike to go to the maximum. We have enough energy from the catalyst to actually push the reaction. And not only that, if you look at this, our time here is longer, but our time has been reduced here. So this is definitely a catalyst. It makes sense to say it's a catalyst. But just to be sure, let's look at other options. If we increase the temperature here on B, you will note that our activation energy will be more, because increasing temperature, we're adding more energy. So we'll have a graph that moves like that. Yes, the reaction can be quicker compared to the first one, because temperature will also make the rate of reaction to increase. But the activation energy now will be much more bigger because we are putting more energy into this reaction. So it's not, temperature is not curve B. If we increase the concentration of the reactants? Well, increasing the concentration of the reactants means that our initial energy of the reactants here will be higher. So our curve will start somewhere here and going up like that. So definitely not this curve. They say the nature of reactants. Well, the nature of the reactants is a characteristic property of the reactants themselves. You cannot really change that. It comes with the reactants. It's how they are. Maybe they're flammable, maybe they're inert, or they're unstable. So you can't change that one. So this doesn't make sense to even be an option. So A seems to be the best option. So 1.5, we're going with A. Now we'll jump to question 1.6. They say here, consider the general chemical reaction. So they've given us a general chemical reaction defined by variables A, B, and C. We have 3A, which is a liquid. We have 2B, which is a gas. And we also have 4C, which is a solid. And you have to notice that this reaction is a reversible reaction because it goes forward and comes back. So that means we take A and B to form C, and C decomposes, it breaks and forms back B and A. Now they say to us here, assume that the reaction is at equilibrium and the chemical reaction is balanced, right? So we assume that the reaction is balanced and also it is at equilibrium. And it makes sense because if it's reversible, it's possible that it can reach equilibrium. Now they say to us here, which one of the following expressions for equilibrium constant Kc is correct? Well, obviously, before I even look at these options, I think I will define my own Kc using the information that is given. It's a quick thing to do, then compare to see if I get the same answer. Kc is going to be defined by the product divided, the concentration of the product divided by the concentration of the reactants, right? But we then take these numbers and put them as a square. But you have to notice that when we define Kc, it is only defined for the aqueous solutions and the gas. If we have a solid like here, we can't put that into our equation. We only put 1. Then we divide by. If we also have a liquid here, we'll put a 1. Then we multiply by. Then here we have a gas, which then now a gas will define it. We'll write the concentration of the gas, which is B to the power 2. We take this and put it as a power, right? This would simply simplify into something like this. And I can see that this is completely wrong because we can't have small brackets here. Wrong as well. This looks right. It looks like what we have. Well, we can't have this because we have solids and liquids, which on the equilibrium equation, we put them as 1. So C is our answer for 1.6. 1.7, they say choose the correct conjugate acid for H2O from the following, right? Now, let's break this question down. If you look at here, they've given us here the conjugate acid. It means these things here are conjugate acids. And it means then now that this is a base. So obviously, to find a conjugate acid, we must add a hydrogen proton, right? We must add a hydrogen proton. Now that means that if I have H2O as my base and I'm adding here a hydrogen proton, right? This will result into what? I'll have 3 hydrogens at the end of the day, right? So this means I'll have 3 hydrogens. But the whole molecule now and the oxygen now, I'll also have my oxygen sitting there. But the whole molecule now, our product here now, will change into a polyatomic ion, right, of positive H. And that is this option here. So our answer is D. Please be sure that you revise the acid base pairs before you step into the exam so that you are able to identify these conjugate base and acids. Now the 1.8 says the diagram below illustrates a galvanic cell. Right? So we know that a galvanic cell uses chemical reactions to generate electricity, right? Now, when we look at this galvanic cell here, we can see that we have our electrode there and another electrode this side, right? These electrodes, they're in a solution here, and the solution, then we also have our salt bridge, which ensures that we have a continuous movement of electrons in here. Now they say here now, consider the following statements regarding the galvanic cell. Sn is the anode and Ag is the cathode. Sn is the cathode and Ag is, okay, so we have those different options and we have to choose which of the above statement is or are true, right? We have to look at those combinations. Now to do this question, I think you need to identify the cathode and the anode, and then you'll be able to know your movement of electrons or the movement of the electricity in this galvanic cell. Now we are going to use here our standard electrode potentials, right? So now if we look at our Ag, I want to find our potential difference here. If we look at our Ag here, right, is given by 0.8. So it's given by 0.8. Then if we look at our Sn, is given by negative 0.14, right? Now when you compare these two numbers, you can see that Sn is more negative, right? Sn is more negative than our Ag, right? What does that mean? That means that our Sn is a cathode, right? Is an anode. This means here, this side here is an anode because it's more negative, is the anode, right? Now this would mean that it will then push electrons away, right? Because it's more negative, it will push electrons away as this reaction occurs here. And these electrons will then get into the wire and travel in the wire coming to this side here, right? So what does this mean? That means this side here, we're actually having an oxidation reaction. This side here, we're experiencing oxidation reaction because we are losing electrons, right? We are losing electrons. And this means this side here, we are gaining those electrons, right? Because they are coming through this side, those electrons. And this means now this side will be a reduction reaction. It will be a reduction reaction, right? Obviously, we know that the anode oxidation takes place in the anode, and reduction cathode reduction reactions take place in the cathode, right? So already I've answered this question. All the three options are there: the anode, cathode, and the movement of the electrons. We can see that the electrons are actually moving from the left to the right, right? So our option here should be Sn is the anode and this is the cathode, right? This cannot be true. And also our electrons flow from left to right. So Roman figure 1 and Roman figure 3 should be our options. So they say here, which one of the above statements or statement is or are true, right? So we said we need to have this and that. So C is our option. 1.9 says in a voltaic cell, electrons flow from the more negatively charged electrode to the more positively charged electrode. Yes, I mean, this is what we have just done now. If this is because we found the value of this to be more negative than the value of that, right, on our standard electrode potential, right? So electrons will move from this more negative to this more positive, right? Electrons move, the other option says electrons will flow from more positively charged electrode to a more negative. No, this is not true. From lower potential energy to higher, no. It has to flow from higher potential energy to low potential energy. That's another option which you don't have, right? In a voltaic cell there must be a movement, right? So A seems to be the correct answer here. 1.9 would be A. The last question says to us, the steam cracking of ethane produces. Well, this is part of the organic chemistry industry, right? Please go and read that chapter before you go to the exam, because you might get an option and a question around that. That part is purely theory that you have to go study and memorize. Well, we know that the steam cracking of ethane, it must give us ethene, or sometimes referred to as ethylene, right? And I can see here they've given me an option of ethylene, right? So the option of that is B. I mean, some of these things you'll get to enjoy them, right, and have fun with chemistry when you have studied, because it's just build up of theory.